Now we'll look at how to figure out bending stress in a beam. Engineers use the word flexural stress, but that just means bending stress. Think of the word flex. Flex means bend. So we're just thinking about bending stress. And as we said earlier, the stress changes over the length of the beam, and what you should be worried about is where is it biggest, because that's where the beam is going to fail, if it's going to fail. Some engineers use this thing called the Flexure Formula. We're not going to use that. I just want to show it to you. We're going to go on and use a simpler version. But I want to show you where the simpler version comes from. So if you're trying to figure out how big is the bending stress in a beam, this formula says the stress is a function of how big is the bending moment, and then what's the deal with the cross-section? What is the moment of inertia of that shape? And think back, that moment of inertia is stiffness of a shape, isn't it? So what is the stiffness of the shape? That's I. And then how far is the distance from the neutral axis out to the farthest place on that beam? And that's C, the distance from the neutral axis to the extreme fiber, they say. Okay, well, we're going to simplify it. Engineers simplify it. They do this too by combining those two shape features, the distance from the fiber and the moment of inertia, and they just say, okay, we're going to call that section modulus. So now this is the last you will see of that flexure formula. We're going on to the simple form right here in the box. The simplified flexure formula is stress equals moment over section modulus. If you pause for a moment and think, you might notice that this formula is kind of similar to our good old basic stress formula. Remember, our stress formula is stress equals force over area. Well, here is stress equals moment over section modulus. Moment is a function of force. Section modulus is a function of the area of the shape. So this is really kind of the first cousin to the stress formula. You don't need to remember that. I'm just saying it. Let's go on and see. So what do we do with this? So section modulus tells you how strong your beam is to resist bending. And it is measured in, its units are inches cubed, inches to the third. And if you want to know how we got there, I did give you a PowerPoint, which is optional. It's the PowerPoint right before this one, Flexure Formula, and it's labeled optional. And you're welcome to go through that and find out why is this inches cubed. I'm not going to weigh you down with a verbal explanation. I'll just leave that for you. So section modulus is a measure of its resistance to bending. Basically, how strong is the beam? So if you have two beams, A and B, and beam A has a section modulus that's twice as big as beam B, then beam A is twice as strong to resist bending than beam A. It's pretty straightforward. Let's look at how we can apply this. And these are now quiz questions. We'll just go through them together. So let's say you have a beam here, a simply supported beam. It's made out of steel wide flange, 18 by 60, and it's 20 feet long, and it's got a 20,000 pound load right in the center. So we figure this stuff out, and we find out that the bending moment is 100,000 foot-pounds right there in the middle. So let's find out the bending stress. Let me just say, if you work for a company that does this sort of thing, they will have easy-to-use software that figures out these bending moment diagrams for you. You will not have to figure out all this stuff. You'll just push the button and poof, it'll spit out these diagrams. So here's our diagram. And we want to find the bending stress. The first thing we'll do is get everything in the same units, so inches, and then we'll just look up our section modulus in the table and we'll be done. So first let's convert this to from foot-pounds into inch-pounds. So right now it's 100K foot-pounds. There are 12 inches in a foot, so we'll say 100K times 12. That'll give us 1200K. Our bending moment, our maximum bending moment, is 1200,000 inch-pounds. If you like to write out all the numbers, which I sometimes do, 100,000 instead of 100K gives you, well, now we're getting a lot of zeros. It's actually 1,200,000 inch-pounds. So for this problem, we might want to keep it in K to keep it simple. All right, and what were we talking about? A wide flange and 18 by 60 pounds per foot. What is the section modulus for this thing? Well, we'll look it up in the table. And I've given you a handout for today, which I think you've seen before, but I gave it to you today again, just to be helpful. And this is a page out of the AISC Steel Manual. And here I've zoomed in on the part of the handout that talks about 18-inch wide flange by 60 pounds per foot. There are a bunch of numbers in this table, sorry, but we are looking for what is happening around the x-axis. That's our bending axis, so we're putting a load down on the top of our beam, and it's going to bend around the middle of the beam. So we're thinking about the x-axis. And we are looking for S, the section modulus. And look here, it says inches to the third, just as we were expecting. So here we are, W18 by 60, chugging on over here to the section modulus column. It says 108 inches to the third is the section modulus for our wide flange. All right, so what is the bending stress? We know the maximum bending moment. We know the section modulus because we just looked it up. And here is our simplified flexure formula. Bending stress is moment over section modulus. Now we just plug in the numbers. 1200K, 1200,000, divided by the section modulus of 108, and that will give you some number. Now let's do a unit analysis. If the bending moment is in inch-pounds, and the section modulus is in inches to the third, we've got inches on the top and the bottom, so one of those inches will cancel out. The inch on the top will cancel out one of the inch times inch times inch on the bottom, and we're left with 1200K pounds over 108 inches squared. Oh, looky there. Does that sound familiar? Pounds per square inch. What we just found was stress. Pounds per square inch PSI. And this number here will be how big is your bending stress in PSI. Yay! Let's try another one. This is our last one. So here we've got a wood beam. It's a timber. It's a big old 8 by 12 timber, and it's 20 feet long with a distributed load on top of 1,000 pounds per foot. It says 1K, and as we know, that means 1,000 pounds per foot. And we found out that the maximum bending moment, well, because it's a distributed load, we're going to get a curve-shaped diagram. And the maximum bending moment turned out to be 50,000 foot-pounds. And we're going to find the bending stress. So first, we'll get those foot-pounds converted to inch-pounds so that everything's in the same units. Then we'll just look up the section modulus in our table. So our bending moment is 50 foot-pounds. There are 12 inches per foot, so 50 times 12 gives us 600 So our bending moment in inch-pounds is 600 inch-pounds. Or if you like to write out the zeros, 50,000 foot-pounds. 50 means 50,000. 50,000 foot-pounds times 12 gives us 600,000 inch-pounds. All right then, what is the section modulus for this 8 by 12 wood beam, this timber? Let's look it up in the table. I have given you another handout. This is actually in the back of our book, if you happen to have the book. This is in the appendix, and he gives you properties for various kinds of lumber. Notice that the sizes start small up here at the top and go down bigger and bigger at the bottom. I'm going to zoom in on this bottom half of the table right here so that we can read it. So here is the nominal size, 8 by 12. Here are a bunch of things, a bunch of characteristics, and right here is the section modulus in inches cubed. There's another section modulus here that you could use if you were doing stuff in metric, but we're doing inches, so we'll stay here. So here, the section modulus for our 8 by 12 is right here, 165.3 inches cubed. Goody. Now we can plug that in to our simplified flexure formula. We know the maximum bending moment is 600,000 inch-pounds. We know the section modulus is 165.3 inches cubed. Let's find the bending stress. Moment over section modulus. We'll plug in the moment, 600. Remember that 600,000 inch-pounds. Very important to remember. That's not just 600. It's 600,000. This is why I sometimes write it both ways on my piece of paper, just because I don't trust myself. I will write 600K blah 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 and figure it out. And then I will go back and I will actually write 600,000 and I will punch that into my calculator. Don't tell anybody I'm doing that because that's probably, I'm probably just being insecure. But I'm just telling you, I do that. Nothing wrong with doing that. All right, anyhow, here's our flexure formula. Stress is moment over section modulus. We'll plug in moment over section modulus. And again, we'll do our unit analysis. There's an inch in the top and an inch in the bottom. The inch in the top cancels out. The inch in the bottom goes from inches cubed to inches squared, because we canceled out that inch. So now we got, look at that, we've got pounds over square inches. In other words, we've got pounds per square inch, or PSI. And whatever number you come up with is your good old stress in PSI. I feel like we're coming full circle.